The last two types of analytical techniques that we're going to talk about are gravimetric analysis and combustion analysis. Let's start with gravimetric analysis. This is where we have some aqueous sample and we usually do a reaction which causes it to precipitate out, meaning we're changing its physical state from being aqueous to solid. Once we crush out the precipitate as a solid, we could filter it off from our reaction and allow it to dry, which then will allow us to separate it. If we have it separated, we can get the mass of our precipitate that we formed. Gravimetric analysis allows us to determine the percent by mass for some component of a compound. So imagine that we have two aqueous solutions, one containing an unknown metal cation with the chloride anion. The other contains aqueous silver nitrate. If we mix these two aqueous solutions together, we'll form silver chloride, which will be a precipitate, and will form the metal nitrate ions that will be dissolved in solution. So what this would look like is we would start with a clear and colorless solution, and as soon as we add the silver nitrate, we would start seeing a white solid precipitate out. That white solid precipitate is that silver chloride. If we were to filter that off and then separate it and dry it, that would be our solid silver chloride. Imagine we want to get the mass of it in order to figure out the percent of chloride in that silver chloride. All of the chloride that we started with in our metal chloride aqueous solution must have ended up in the silver chloride precipitate. So we can work backwards to figure out how much of the chloride was in our unknown metal chloride initially. A 0.8633 gram sample of an ionic compound containing chloride ions and an unknown metal cation is dissolved in water and treated with an excess of silver nitrate. If 1.5615 grams of the silver chloride precipitate forms, what is the percent by mass of chlorine in the original compound? So just like we saw before, we have some metal chloride reacting with silver nitrate, that's aqueous. This would be a double replacement type reaction where we're forming silver chloride as a precipitate, and then our spectator ions would be our metal nitrate, which would be aqueous. The first thing we want to do is start at the bottom. We know we formed a silver chloride precipitate, so can we write the net ionic equation for the formation of our silver chloride precipitate? Silver chloride must have been from the combination of aqueous silver ions plus aqueous chloride anions. So starting with our net ionic equation, we know how much of our silver chloride we formed, 1.5615 grams. If we can figure out how much chloride is in our silver chloride, that will be exactly the same amount that was in our metal chloride unknown to begin with. When we solve for the percent by mass in the original compound, percent by mass of chloride will be found by determining the grams of chloride divided by the grams of the sample. And then since it's a percentage, we'll multiply by 100. We were told the initial mass of the sample was 0.8633 grams. So what we really need to find in this problem, in order to answer it, is how many grams of chloride ended up in our silver chloride. And we can use stoichiometry to solve for this. If we know the mass of our silver chloride precipitate, we can use our balanced net ionic equation to solve for how many chloride ions were in there. So starting with our 1.5615 grams of AgCl, if we're going to use our balanced equation, the first thing we have to do is convert our grams to moles. So calculating the molar mass of silver chloride, and 1 mole is 143.37 grams for silver chloride. Using our balanced net ionic equation, every 1 mole of AgCl that forms 1 mole of chloride ions reacted. And then we want mass of chloride. So 1 mole of chloride, whether it's chloride ions or neutral chlorine, from the periodic table is 35.5 grams. Our grams of silver chloride will cancel. Our moles of silver chloride will cancel. Moles of chloride ions cancel, and we're left with our mass of our chlorine, which we should get 0.387 grams of chlorine in our sample. And so we're going to plug that into our numerator of our fraction, 0.387 grams, divided by the sample mass, which was 0.8633 grams, times 100. That'll tell us our percentage by mass of chlorine in our unknown and in our precipitate sample, since they're the same. And that should come out to 44.8% chlorine. Let's try another gravimetric analysis problem. An unknown ore contains lead. A sample of the ore weighing 1.526 grams was treated with nitric acid, which dissolved the rock. The resulting solution was filtered and required 29.22 milliliters of 0.122 molar sodium sulfate to completely precipitate all of the lead as lead sulfate. How many grams of lead were in the sample, and what was the percent by mass of lead in the ore? It's easy to get lost in the verbiage of this problem. It's easier to start at the bottom and work our way back up. We know that all of the lead ended up as a solid precipitate in the form of lead sulfate. So gravimetric analysis problems are easier to start with a net ionic equation. The two things that had to come together to make our lead sulfate would be lead 2+ ions from the aqueous solution and sulfate anions from the aqueous solution. The sulfate anions would have came to us in the form of the solution sodium sulfate. In this example, the sodium just happens to be a spectator ion, so we don't need to worry about that. But we do know the molarity, 0.112 molar, and the volume, 29.22 milliliters, of our sodium sulfate solution. Sodium sulfate, when in water, gives us 2 sodium ions and 1 sulfate anion. So if we know the concentration of our sodium sulfate and the volume, that's going to be exactly the same as the concentration and volume of our sulfate, because those two are 1-to-1. So this is a little bit different than the last one because we have a titration that took place where we know the volume and concentration that we're going to use to get at the number of moles of sulfate. If we can get at the moles of sulfate, we can use our balanced net ionic equation to work backwards to the moles of lead. And from there we can figure out the grams of lead. We're still figuring out a percentage by mass at the end, so we're going to still have to calculate our percent by mass of lead will be our grams of lead divided by the grams of our sample times 100%. That's going to be our final step. And just like last time, we always have to be told the mass of our sample. The total mass of our sample was 1.526 grams. So we are working to figure out the grams of lead first. Starting with our sodium sulfate, we know the volume that was used. If we put that into liters, 0.02922 liters, and multiply by the molarity in units of moles per liter, 0.122 moles of sulfate per liter. Our volume will cancel and we're left in moles of sulfate. From here we can use our balanced net ionic equation. 1 mole of sulfate reacts with 1 mole of lead 2+ ions. And using the atomic mass off the periodic table, 1 mole of lead is equal to 207.2 grams. Our moles of sulfate will cancel, our moles of lead will cancel, and this is how we'll find the mass or the grams of lead in our sample. When we calculate, we should get 0.74 grams of lead that was in our ore, and that's how much ended up in our solid lead sulfate. Finally, plugging that mass into our percent lead, 0.74 grams divided by the mass of our sample will give us our percent by mass of lead, which should come out to being approximately 48%. Combustion analysis is a method of indirect analysis for determining the empirical formula of a compound. If you think back to chapter 3, when we first started learning empirical formulas, we were given either the grams of all the elements in the compound, or we were given their percentages, which we could cross off and assume were the same as grams. With indirect analysis, we're not given those masses directly. The compound is reacted with oxygen and turned into other compounds. We will work backwards from those other compounds that are formed in order to determine what the starting atoms were. Let's look at an example of how combustion analysis works. If we have a compound that is made up of carbon, hydrogen, and oxygen, or just carbon and hydrogen, and it's combusted with oxygen in the atmosphere, the products are always going to be carbon dioxide and water. So for example, if we have methanol, which is made up of only carbon, hydrogen, and oxygen, and it's reacted with oxygen, the two products are going to be CO2 and H2O. All of the carbon in the initial sample must have ended up in the CO2. So we can use our amount of carbon dioxide that we know to work backwards and figure out how much carbon was in our unknown. For the water, all of the hydrogen ended up there. There's hydrogen in our original sample, and it all is in the water. If we know the mass of the water, we can figure out how much hydrogen was in our original sample. And for the water, we'll have to be a little bit different because we have oxygen that ended up in CO2 and oxygen that ended up in water. But that's not all the oxygen that was from our original sample. Some of it could have came from the combustion process where oxygen was added. A setup for this would look like we have our sample being burned in some chamber. There's an inlet source for oxygen. And we have two different things that can absorb either carbon dioxide or water. Calcium sulfate will be a dry compound that will absorb all the water that's formed. If we take a mass of the calcium sulfate in this tube before the reaction and take a mass of it after the reaction, the difference in mass will be how much water the combustion created. Sodium hydroxide will absorb all the carbon dioxide formed. Sodium hydroxide is a base and carbon dioxide is slightly acidic. Same principle, if we take a mass of all the sodium hydroxide initially, do the combustion, and then see how much carbon dioxide is formed by taking a mass after, we can determine a mass of CO2 that was formed from the reaction. Calculating an empirical formula from combustion analysis. A 0.5438 gram sample of a pure liquid consisting only of carbon, hydrogen, and oxygen was burned in pure oxygen, and 1.039 grams of CO2 and 0.6369 grams of H2O were obtained. What is the empirical formula of the unknown compound? So we have some sample with carbon, hydrogen, and oxygen in it. And remember, when we're finding an empirical formula, we don't know what these subscripts are. That's going to be our job to figure them out. Combustion means it's being burned in oxygen, and our two products are going to be carbon dioxide and water. Now we can't write a balanced chemical equation because we don't know what our unknown is yet. But we do know a few things. We know that we can start with our mass of carbon dioxide, which is 1.039 grams, and all of the carbon that ended up in our carbon dioxide must have came from the carbon in our sample. Next, we can start with the mass of our water, which we were told was 0.6369 grams, and all of the hydrogen that ended up in our water must have came from the hydrogen in our unknown sample. So let's just start with our carbon dioxide mass. 1.039 grams of CO2 were formed. And if we're going to do any mole relationships, we're going to first have to convert our grams of CO2 into moles of CO2. And 1 mole of carbon dioxide is 44 grams. Now, looking at our formula for carbon dioxide, for every 1 mole of CO2, there's 1 mole of carbon, and for every 1 mole of CO2, there's 2 moles of oxygen. Recall we can look at the subscripts in a chemical formula to write mole-to-mole ratios. We're interested in carbon right now, so we can say that 1 mole of carbon dioxide is equivalent to 1 mole of carbon. Next, we can convert our moles of carbon into grams of carbon, and 1 mole of carbon is 12.01 grams. Our grams of CO2 cancel, our moles of CO2 cancel, our moles of carbon cancel, and our mass of carbon that ended up in the carbon dioxide is 0.284 grams of carbon. Next, let's start with our water and do the same thing. We want to figure out how much hydrogen ended up in our water. We have 0.6369 grams of H2O. Convert our grams of water into moles of water. 1 mole H2O is 18 grams. And in every 1 mole of water, we want to figure out the relationship of hydrogen to that. So looking at the subscript here, there's a 2 after the hydrogen. That means in every 1 mole of water, we can say that there's 2 moles of hydrogen present. And then lastly, converting to grams, 1 mole of hydrogen is 1.01 grams. Our mass of hydrogen that ended up in our water is 0.0715 grams of hydrogen. The reason we needed to convert to grams of our carbon and our hydrogen and not stop at moles is because we need to figure out how much oxygen was in our unknown. In order to do that, we need to take the mass of our sample initially, because our 0.438 gram sample contained carbon, hydrogen, and oxygen. If we subtract off the mass of carbon and hydrogen, what we'll be left with is the mass of the oxygen. So we'll subtract off 0.284 grams of carbon plus the 0.0715 grams of hydrogen. The difference that we get, which is 0.188 grams, is our mass of oxygen. Now, whenever we figure out our subscripts in our unknown, our subscripts are really mole ratios. So we're going to need to know the moles of carbon, the moles of hydrogen, and the moles of oxygen. And we had to find the smallest whole number ratio. So now that we know the mass of our carbon, hydrogen, and oxygen, we can convert all of those values into moles. For carbon, we're going to want to divide by the atomic mass, which is 12.01 grams. For hydrogen, we're going to divide by 1.01 grams. And for oxygen, we're going to divide by 16 grams per mole, giving us our moles of carbon, 0.0236 moles, our moles of hydrogen, 0.708 moles, and our moles for oxygen, which should be 0.0118 moles for oxygen. So notice we had our grams cancel for all of these, and we were left in units of moles. Now that we have our moles of our carbon, hydrogen, and oxygen, the next step in order to find an empirical formula was to divide by the smallest number and see if we got a whole number small ratio. In this example, the smallest number of moles is for oxygen. So we're going to divide all of our mole values by the moles of oxygen, which is 0.0118. When we divide the oxygen moles by itself, that'll give us 1. When we divide by the moles of hydrogen, we get 6. And when we divide by the moles of carbon, we get 2. Now, since we got small whole numbers, those are going to tell us our subscripts in our unknown formula. So we got C2H6O. That will be equal to our empirical formula of our unknown compound. And just a refresher on how to find the true molecular formula after you've figured out an empirical formula. So in the previous example, we found the empirical formula was C2H6O. If the molecular mass of the true compound was found to be 138 grams per mole, what is the molecular formula? So we had to take the molecular mass and divide by the empirical formula mass to figure out how many empirical formula units were contained within our molecular formula. Once we knew the number of units, we could multiply our empirical formula through by that number. So our empirical formula was C2H6O that we determined. We need to find the empirical formula mass. So what is the mass of our C2H6O? Our empirical formula mass can be calculated 12 times 2 for the carbon, plus 6 times 1 for the hydrogens, plus 16 for the oxygen. And so that would give us 46 grams per mole. Figuring out the number of empirical formula units, our molecular mass was given to us 138 grams per mole divided by 46 grams per mole, and that gives us 3. We need to take 3 and multiply it through by C2H6O, and that will give us our molecular formula, C6H18O3. A combustion analysis of a 0.44 gram sample of an unknown compound containing only carbon, hydrogen, and oxygen yields 0.88 grams of CO2 and 0.36 grams of H2O. If the sample has a molar mass of 132 grams per mole, what is the molecular formula of the sample? So before we can find the molecular formula, we first have to find the empirical formula. We know our compound is composed of only carbon, hydrogen, and oxygen, and it's our job to determine what those subscripts are. Combustion means it's being reacted with O2, and we're forming carbon dioxide and water as our products. We were told our mass of CO2 was 0.88 grams, and our mass of H2O was 0.36 grams. We're going to start with our mass of CO2 and work backwards to figure out how much carbon was in the sample. And we're going to start with our mass of H2O to figure out how much hydrogen was in our sample. By subtracting from the total sample size, which was 0.44 grams, is how we'll figure out our amount of oxygen. So let's start with our mass of CO2. We have 0.88 grams of CO2 that was formed. We need to convert our mass into moles. The molar mass of CO2 is 44 grams per mole. And we're working with the carbon dioxide to figure out the amount of carbon. So 1 mole of CO2 is 1 mole of carbon. Right now, our grams of CO2 cancel, our moles of CO2 cancel, and we're in moles of carbon. We're going to want to figure out what the mass of our carbon is, though. So 1 mole of carbon is about 12 grams. Now our moles of carbon will cancel. And our grams of carbon is going to be 0.240 grams. Next, we need to figure out how much hydrogen ended up in our water. So starting with 0.36 grams of H2O, convert our mass of water into moles of water using the molecular mass. And 1 mole of water is 18 grams. 1 mole of water is 2 moles of hydrogen, looking at our subscript in the formula. And then converting our moles back to grams, 1 mole of hydrogen is about 1 gram per mole. And so our mass of hydrogen in our sample is about 0.0404 grams of hydrogen. We're going to need to subtract in order to figure out the grams of oxygen. So starting with our total sample mass, which was 0.44 grams, we're going to subtract off the sum of the mass of the carbon plus the mass of the hydrogen to give us our grams of oxygen. So 0.44 minus 0.2804 gives us 0.1596 grams of oxygen. We can't work backwards from the amount of CO2 to oxygen and then the amount of H2O to oxygen because there was additional oxygen introduced when we combusted it. So now that we have the mass of everything, let's convert our grams of carbon to moles of carbon. Take our grams of carbon and divide by 12 grams per mole to give us about 0.02 moles of carbon. Take our grams of hydrogen and divide by the atomic mass for hydrogen, which is 1.01 grams, to give us about 0.04 moles for the hydrogen. And starting with our grams of oxygen, the atomic mass for 1 mole of oxygen is 16 grams, and that gives us 0.0098 moles of oxygen. Pick the one that is the smallest number of moles and divide everything by that, and that looks like the oxygen, so divide by 0.0098 moles, and that'll give us 1 for our oxygen. Divide the hydrogen by 0.0098, and for our hydrogen that should give us 4. And for our carbon, divide by 0.0098, and that gives us 2 for our carbon. Those are going to be our subscripts that we're going to plug into our unknown. So we got C2H4O1, and that would represent our empirical formula. So our empirical formula was equal to C2H4O. We want to find the molecular formula. So we need to calculate our empirical formula mass if we're going to find our molecular formula. Our empirical formula units will be equal to our molar mass divided by our empirical formula mass. We had to be given the molar mass in the problem in order to do this final step. 132 grams per mole. And if we calculate our empirical formula mass, we're going to take 2 times 12 for the carbon, plus 4 for the hydrogens, plus 16 for the oxygens, and we're going to get 44 grams per mole. And when we divide, that tells us that there is going to be 3 empirical formula units in our true molecular formula. So we'll do 3 times our empirical formula, C2H4O, and that gives us our molecular formula equal to C6H12O3. And that would be our final answer for this problem.